Hey guys, welcome to another IGCSE revision video. Today we're finally starting on IGCSE Physics. I'm not actually going to be going through the larger topics in order. I think there are 5 main big topics that you need to cover in the syllabus, and we're actually going to be starting from magnetism and electricity. I have had some people say that they are having a bit of difficulty with this particular topic, so this is what we're going to be starting with. So here is a quick look at the syllabus content for today's video, so have a quick read through and we will begin shortly. So, magnetism. Well, magnetism, of course, has something to do with magnets. So, magnets are made of ferromagnetic material. The main things that you will come across in your course would be iron and steel. And all magnets have a north and south pole, and these poles can either attract or repel depending on the interaction. Now, when you have opposite poles, for example, north and a south pole, they will always attract. If you have two same poles or like poles, they will always repel. So opposites attract and same poles repel. That's a very, very important concept. And so ferromagnetic materials, which of course are what magnets are made of, are special because they have smaller magnetic units within them called domains. And these little magnets or magnet units called domains each have a north and south pole as well. And that is sort of the easiest way to sort of demonstrate this idea. Now, in a non-magnetized ferromagnetic material, for example iron, right? So just because something is ferromagnetic doesn't mean that it is automatically a magnet. But if something is a magnet, then it has to be a ferromagnetic material. Do you see what I mean? And so in a non-magnetized piece of iron, which is of course ferromagnetic, you've got these little domain magnets inside the iron that are randomized in orientation. They're sort of facing all over the place, and they don't really have any sort of unified direction, right? And that is essentially why the iron is not a magnet, but it is ferromagnetic, suggesting that it has a potential to become magnet. And we'll talk about induced magnetism later, but for now, just understand that in a non-magnetized magnetic material, the domains, or the little magnetic units inside of them, are basically randomized in orientation. Now, in a permanent magnet, you have these domains that are all unified in a particular direction, and as you can see in this right diagram here, all the little domains have their north poles facing a certain direction and the south poles facing the opposite direction. And therefore, if you sort of combine that all in together and you look at the bigger picture, you see that the left side here is basically the south pole of the entire magnet, and the right side here is the north pole, and that is all dictated by the unified orientation of the domains inside the magnet. So let's take a look at what induced magnetism is. So basically, by placing a magnet near a piece of iron, which I said again is ferromagnetic, the iron will become magnetized. And this is because the magnet will actually cause the little domains in the iron to align themselves via the interaction of magnetic field from the magnet. Right, so here, let's just take a look at the diagram, right? So if you put an iron, right, these little domains here, the green is south pole and the red is north pole, just like the diagram below here. Green south, red north, green south, red north, right? So you've got these little domains. Now, if you initially, of course, all the domains will be randomized, as I said, in iron, which is not a magnet, at least quite yet. If you put a permanent magnet like the one over here on the right next to a piece of iron, these little domains will actually orientate themselves. As again, I said that opposite poles will attract each other. So if you've got a permanent magnet with a south pole right over here, then these little domains will all orientate themselves so that the North Pole is attracted towards the South, so hence you get the alignment of the North Pole towards the right and the South Pole towards the left. And ultimately what that means is this ion will always get attracted to the magnet because the domains will align themselves because of the magnetic field from the permanent magnet. And so because the entirety, if you look at the entirety of the iron piece here, the North Pole inherently will be towards or attracted to the South Pole here, so therefore you'll get that attraction. Oppositely, if you were to have it the other way around and you have a permanent magnet with a North Pole facing this way, then of course the little South Poles of all the domains will align towards this end here, and the North Pole will face away. And so ultimately what this permanent magnet is doing when it's near the iron piece is magnetizing it. Because the domains are aligning themselves, they are turning into a magnet with a magnetic field on its own, and therefore you get this attraction happening. Okay? And so if you take a look at this diagram over to the right here, this is a very practical example of how induced magnetism works, right? So if you put two iron nails next to each other, you will never get them being attracted to each other. There's absolutely no force, and that's because they aren't magnets quite yet. They don't have any sort of magnetism. But as soon as you have some sort of magnet, right, let's just say North and South Pole here, then the iron will attract itself onto the magnet, and as I said, the induced magnetism will cause this top nail here. The South Pole will of course be at the top, closer to the North Pole of the permanent magnet, because again, the opposite poles will attract each other, and if this top part is the South Pole, then the bottom part must be the North Pole. And you can actually see that the second iron will actually, or the second iron nail will actually get attracted onto the first nail, because the first nail now has become a magnet. The first nail induces magnetism onto the second nail, and so the top part of the second nail will have a South Pole and the bottom part of the second nail will have a North Pole, and so therefore you get an attraction between these two nails, because they are now magnets, because the first nail has basically been magnetized by this top permanent magnet. Okay, so but if there was no sort of induced magnetism going on there, then the two iron nails would never actually attract each other, right? So essentially the idea is that using a permanent magnet you can magnetize or induce magnetism in these iron nails, which are of course ferromagnetic and have these little domain magnets sitting inside of them. Now, iron loses magnetism very, very quickly. So soon as you detach the permanent magnet from the first nail, this whole thing falls apart, because both nails, well, the first nail essentially loses all of its magnetism, and the second nail also loses all of its magnetism as well as a result. And so iron as a substance loses magnetism very, very quickly, so when it does get induced with magnetism, it becomes a temporary magnet, right? However, steel, which is of course largely made of iron but other things as well like carbon, retains some of the magnetism without losing it completely. So once you magnetize steel, even after you sort of detach the permanent magnet away from the steel, it will still have some sort of magnetism left unless you demagnetize it by, hammering it or whatever. We'll take a look at demagnetizing things later. But the idea is steel can retain magnetism and become a permanent magnet, whereas iron will only be a temporary magnet because it always loses its magnetism very, very quickly. And so I suppose the important thing here would be to understand how to draw magnetic field lines. I think this first image is probably the most important for you because this bar magnet is what we are all familiar with. A bar magnet, as with any other magnet, will have a north and a south pole. And so if you draw the field lines horizontally, you'll always get the field lines going from the south to north. But if you look at the top rays here, it'll be going from north to south, right? So this middle chunk here, the rays, the magnetic field lines will always go from north to south, but the ones at the ends will always go in the direction of south to north. So just memorize how this looks. And you should always probably know how the magnetic field lines look when the poles are either attracting or repelling, right? So opposite poles attract, and it'll always go from north to south, like this diagram here. And if you're looking at two of the same poles, they're obviously going to be repelling each other, and you get this sort of field line happening here. So make sure you are very comfortable drawing this out, and have a look at this diagram and just memorize it the best that you can. Now, experimentally, you can actually demonstrate these magnetic field lines. First of all, you can either use a compass. So if you put like a compass in series like this around a bar magnet, the compass will actually point towards the direction of the field lines, like so. And secondly, you can also use iron sort of fillings, which are very fine iron particles, and scatter it all over the place, and they will sort of align themselves along with the magnetic field lines. So, this entire topic is, of course, electricity and magnetism, and we will combine the two in a second, but some important concepts here, right? So, electricity is basically the flow of electrons, and it would make sense that because of that, electrons will flow from a negative charge to a positive charge. But current is a little bit different. Current is defined as the flow of positive charge, which is from positive to negative. So if you have a look at this right diagram here, this side is negative, so you would expect the electrons to be flowing in this particular direction. But when you're thinking about current, it's actually going the opposite direction, because it's the flow of not negative but positive charge. So it's always the opposite way around. Now, current is what we use mainly in calculations and things like that. So if they ever were to give you a direction of electron flow, then you will have to really understand that current, on the other hand, is going the other way around, and then you'll have to sort of go from there. But we will look at that in a bit more detail afterwards as well. So, while we're on the topic of electricity, of course, current flowing through a wire also magically produces a magnetic field. A magnetic field around a coil of wire will produce a magnetic field that is very basically identical to what we saw of a bar magnet, right? So let's go through the magnetic field through a straight wire on the left hand side first, right? So current, again, is going upwards, but the flow of electricity, or the flow of electrons, is going downwards. But anyway, current, we are going to suggest that it's going up. And so if we point our thumb, right, this is called the right hand grip pull, like as the diagram shows here, point your thumb towards the direction of the current, and the fingers which wrap around the wire will give the direction of the magnetic field that the wire produces. Now, if you were to get a long wire and coil it up like this diagram in the middle here, then it will produce the magnetic field just like a bar magnet. So again, as we took a look at before, the horizontal lines in the middle is going from left to right here. Oh, sorry, right to left, going in that direction. And so remember, in a bar magnet, it goes from the south to north pole. So if you were to take a look at the poles of the magnetic field that this thing produces, then you can sort of judge by the field lines that this side here to the right is the south pole and this side here is the north pole. But even if I didn't give you these field lines and the direction of field lines, you can actually tell which side will be the north and which side will be the south pole just by looking at the direction of current in the ends of the coils. So if you take a look at this left hand side here, and imagine if you are looking at it from a head-on, straight-on perspective, you can see that the electricity is actually going in an anti-clockwise direction, or current is flowing anti-clockwise in the wire. So take a look at this left diagram here. You can see that this is the sort of direction of the current that you'll see in the end of the coil on the left hand side here. And so an easy way to memorize that would be that it makes the shape of an N here, and therefore north. On the other hand, if you look at the right hand side of this coil of wire, you will actually see that the current is flowing clockwise. And so if you take a look and see the shape that it makes, it's sort of like an S shape here, right? And so that would suggest that it is the south pole in that end. So that is a pretty handy way of knowing the north and south poles created by the magnetic fields of a coil of wire carrying a current in a certain direction. What's really important to note here is that, again, the north and south poles created by the coil of wire is solely dictated by the direction of the current, right? So if you look at one end and it's going anti-clockwise, and again that's the north pole. If it's going clockwise, it's the south pole. So we will take a look at that in this section here. But first of all, magnetization. If you want to magnetize a piece of steel or something like that, one way of approaching that would be by stroking it with a permanent magnet in a sort of circular direction here, so that you are overall sort of nicely aligning all the domains in the steel bar so as to induce permanent magnetism in the steel bar. But as I was saying before, electricity-wise, you can also magnetize metal, or steel or iron or whatever, by placing a solenoid, which is basically metal inside a coil of wire like the setup here, with direct current. And direct current means that the current is always going in one direction. Okay, alternating current is when the current is changing directions all the time, constantly. But direct current is so in one direction all the time, and that's obviously very important, because if you want to magnetize a bar of steel or whatever using the magnetic fields of a coil wire, which we talked about before, then it needs to have a consistent north and south pole. Otherwise the magnet will, or the steel will never get magnetized, and that's why direct current is really important here. And so the electron flow is going upwards, but again, current will be going the opposite direction. So if you take a look at this particular diagram here, I've labeled current going down, and if you use the tip I told you before, we can see that in this end here it's going anti-clockwise, on this end here it's going clockwise, so therefore you have the north pole on the left hand side and the south pole on the right hand side, and that magnetic field produced by the coil will inherently induce magnetism in the metal inside the coil, which is what we call a solenoid. And this setup is essentially what the theory behind electromagnetism is. Right? Electromagnetism is basically generating magnetism by electricity, which is what we're doing here. And this is actually quite useful. And for example, when you're moving scraps, scrap metals and things like that, in those metal scrap yards, they use this theory. And so as soon as you turn off the electricity, then the entire setup loses magnetism and therefore sort of drops the scrap. But if you want to pick it up again, you simply turn on the electricity and it generates the magnetism, and it it picks up the scrap metals, and you can sort of transport it and things like that. So that's quite handy. So if we take a look at the ideas of magnetizing something, you can also demagnetize something. And if you want to demagnetize a permanent magnet, you can either heat it like crazy, and all the little domains will start to start misaligning itself, because essentially permanent magnets, the only difference between permanent magnets and a ferromagnetic material that isn't magnetic quite yet is that the domains are not aligned. Okay, so if the domains are well aligned, then it's basically a magnet. If the domains are all random, then it's not a magnet, essentially. So heating it and hammering it, physical impact, all those things will misalign the domain particles inside the magnet and therefore demagnetize it. You can also use alternating current, right? Again, alternating current means the current is always changing directions, and that means the north and south pole of the magnet or the magnetic field produced by the coil of wire, it's always constantly changing, and that again will just aim to mix up all the domain units in terms of its orientation, randomize everything, and therefore causing the magnet to lose its magnetism. So finally, permanent magnets are designed with hard magnetic material and used for purposes where magnetism is needed for a very long period of time. Of course, with this you don't have the option of just switching it off. But electromagnets, as I said before, use a solenoid, which is the metal that you put inside the coil of wire, to create a magnetic field, and it is used when a magnetic field can or needs to be sort of turned off and on, like for example when you are moving metal scraps, and that is very handy. So that is it for today, guys. Please visit www.freeexamacademy.com for comprehensive notes. Like, share, and subscribe to help this channel grow. I very much appreciate all your support, and please think about joining Patreon. I've got some exclusive IGCSE content there if you like, but otherwise I will see you in the next video. Cheers.